All right, so example 1, 7.5, it says in triangle JLN, JLN is the biggest triangle, if LN equals 9.6, so they're telling me this measurement here is 9.6. What are LM and MN? So LM, let's call that X, and MN, let's call that Y, are the sides divided proportionally. Okay, so first off, what we got here that we haven't seen yet in these problems, we have overlapping triangles, we've got parallel lines happening here. We go back to our parallel lines cut by transversal properties that we learned back in chapter 3, I believe is what it was. When parallel lines are cut by transversal, so KM, JN parallel lines, LJ transversal, the corresponding angles are congruent, and this angle up here, LKM, this angle down here, angle J, are corresponding angles for that transversal. And on the same reasoning, LN's a transversal for the same pair of parallel lines, which means that LMK and angle N have to be congruent to each other because they're corresponding angles for that transversal. Which leads me to the fact that the top triangle here, which I'll make blue, this triangle here, which is LKM, is going to be similar to the big triangle LJN, or JLN, or whatever you want to call it. So the blue triangle and the red triangle are similar to one another by angle-angle similarity. And on top of this, the fact that these two angles match those two angles makes them similar. This angle on top, right here, is shared by both the smaller and the bigger triangle, so it's actually angle-angle-angle similarity if you go that far. Now, with that in mind, let me just change the color here. Make that red. So, this side here, this 9.6, is the length of this big triangle. And LJ, which is going to be 8, is the length of this side of this triangle. Those two sides are proportional to the smaller sides, 3 and X, in the smaller triangle. And if you look at similarity of pieces, I could keep it in the current state it's in, or I could separate it into two separate triangles if I'm having trouble seeing it. But if I'm looking at the angle with 2 marks, which is opposite LJ, that should be proportional to the angle with 2 marks in the smaller triangle, which is LK. The angle with 1 mark over here, angle J, is opposite side LN, so that side LN is proportional to the shorter side opposite 1 marked angle here, X. So that's the relationship of sides in these similar triangles that allows us to create a proportion. So if I do make my proportion, I'm going to put the small measurements on top, so X and 3 are the sides I'm dealing with here, so X on top, 3 on top. Side X in the small triangle corresponds to side 9.6 in the big triangle, so 9.6 goes in the same fraction. And side 3 on the short triangle corresponds to side 8 on the big triangle. And just like that, we have the capacity to figure out what X equals using that proportion. So if I cross multiply, 8 times X equals 9.6 times 3. If I divide both sides by 8, I end up with 3.6. So X equals 3.6. Our task was to find the length of LM and MN. LM is what we just found, right? So I'm going to write over here LM equals 3.6. I really like using a letter like X to refer to something I don't know, but then when I actually identify the answer, I want to identify it for what it actually is. So LM, that's what they asked us for, right? The other thing they asked us for is MN. Well, once I know that LM is equal to 3.6, once I know this information, and I know the whole side is 9.6, these two small pieces make the big piece, right? So 3.6 plus y we don't know yet is equal to 9.6. So y would equal 6. and y is representing mn, the other thing they asked me for, so mn equals 6. The other thing they asked me to do on this problem is to state whether the sides are divided proportionally. So I'm going to erase all the markings I got on here real quick, just to pinpoint what they're talking about here. So this side's 3, this piece is 3, this piece is 5. So 3 goes from here to here only, and 5 goes from there to there. This piece here is 3.6, and this piece here is 6. They're questioning whether these pieces are proportional to these pieces. We're looking for a proportionality statement there, and we need to verify if they are or aren't, so to answer this question. So if I look at 3 over 5, can I reduce 3 over 5? No, that's as reduced as it can get. So I need to see if 3.6 over 6 reduces to 3 over 5. And if you recall what I showed you the other day with these common ratio ideas, we want all the fractions to be reduced to lowest terms in integer form. A lot of times we get decimals in these fractions. So if you make both the top and bottom have equal number of decimal places, drop the decimals off. So 36 over 60 is the same as 3.6 over 6. Then reduce if possible. Can everybody see both numbers divided evenly by 6? So 36 divided by 6 is 6. 60 divided by 6 is 10. And 6 and 10 are both even. They divide by 2. 6 divided by 2 is 3, and 10 divided by 2 is 5. So the ratio of these sides is 3 to 5. The ratio of these sides is 3 to 5. So these sides are divided proportionally. All right? So are the sides divided proportionally? Yes. Okay. And that leads us into a new theorem that's in this section called the side splitter theorem, which simply states in overlapping triangles, if the bases are parallel to one another, the sides created by the split are proportional to one another. So this over this equals this over this. Every single time that's true. All right, so we can make that assumption. Whenever we see this picture, we see the parallel lines immediately. These pieces are proportional to those pieces. It has nothing to do with the parallel pieces. Those are not proportional to these. All right, similar triangle will help us get these pieces here, but these pieces proportional to those pieces always works.